everybody, this is a little quick mini video to review electron configuration. And we're going to talk about building electron configurations. We are going to talk about noble gas electron configurations, and we are going to talk about orbital diagrams, ions, and a few other things. So for my students, this should be a review because we did do some of this in class, but I am going to try to go step by step and go, a little bit slowly for anybody who might need some extra help. So when we're looking at this, number one, we are going to need to look at the periodic table. And because of the fact that we are right now for the beginning here doing electron configurations of atoms, atoms are neutral. So the number of electrons equals the number of protons. So we are going to get the number of electrons from the atomic number. So for example, if we want to do the electron configuration of bromine, we're going to need to find bromine on the periodic table. And bromine on the periodic table is element number 35. So we need to fill 35 electrons in our configuration. And down here I have the diagonal rule that I use when following the Aufbau Principle, which basically says that we're going to go in order of lowest energy to highest energy when we add our electrons. Now, Aufbau is not perfect, but it works for the most part. It's pretty close to being perfect, and it's the most perfect thing that we have that we can predict our electron configurations with. So if I want to do my full electron configuration, I'm going to look also and see that bromine is in period 1, 2, 3, 4. So I am not going to have anything past the fourth principal quantum number. That front number of 4 is the highest number I will have, so I don't even need the bottom of this chart. I also know, right, that these here are in my S block. This is my P block. This is my D block. And this is my F block. So those are the sublevels that are filling when I go through all of those. So for example, when I go through and I go from hydrogen to helium, I go from 1s1 to 1s2. 1s2, 2s1, 1s2, 2s2. Then I go 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6. Then I add on the 3s2. Then I add on the 3p, 1, 2, 3, 4, 5, 6. 4s1, 2. 3d, 1 through 10. And then it goes back to 4p, 1, 2, 3, 4, 5. So that would be one way to figure out the electron configuration. If you are unable to follow it on the table, we're going to do it with the diagonal rule. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And I'm going to keep doing this until my top numbers add up to 35. 3d10, 4p5 is what gets me there. So again, bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. These superscripted numbers are the numbers of electrons, and they add up to 35. Now, that is called the complete electron configuration. Sometimes that complete electron configuration is not very user-friendly, especially when we get to elements with lots and lots of electrons. So we are going to do what is called the noble gas configuration. The noble gas configuration puts the symbol of a noble gas in brackets, which represents all of that noble gas's electrons. And then all we have to do is add the electrons after that. So we look on the table. Bromine has an atomic number of 35. We are looking for the noble gas that is less than 35, but closest to it. That's going to be argon. Argon, that represents the first 18 electrons. That means I only need 17 more. I go through argon. As I know, this is period 1, period 2, period 3. So argon gets us to 3p6. I need 17 more electrons, which gets me to 4s2, 3d10, 4p5. Now remember, you can write these in order of filling or in order of energy level, as long as you know that the 3d is inside of the 4s. The energy is higher, but the location or the average distance from the nucleus is closer. Now, if we want to do a different element, do one more of these, like chromium. Chromium has an atomic number of 24, which means that I need to find chromium on the periodic table, number 24. For the complete electron configuration, 1, 2, 3, it's in period 4. So we can't go past the first principal quantum number being 4. It's past hydrogen and helium. It's all the way through period 2. It's all the way through period 3, which means that now we're going to go to 4s, and we're going to have some number of 3d electrons. 1, 2, 3, 4. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That gets us to 2, 4, 10, 12, 18, 19, 20. 3d4 gets us to 24. Now, there are some exceptions on the periodic table. This video is only for the strict followers of Aufbau. Okay, this is just for the strict followers of Aufbau. And chromium doesn't actually exist like this. Chromium is an exception, which is 4s1, 3d5, but for AP chemistry, you wouldn't be asked that. AP chemistry wants you to be able to follow the trend and wants you to be able to follow the rules for this. So the actual configuration of chromium is not what we get when we do the Aufbau principle with the diagonal rule, but that's okay. For AP, they wouldn't ask you to do any of the exceptions. So now to do the noble gas configuration, I find chromium is in period 4. I look for the noble gas that has an atomic number lower, but the closest one to it, which means that argon is going to be in brackets. Argon represents these first 18 electrons, 2, 10, 12, 18, and what is left comes after it. It would actually be 4s1, 3d5, okay? But again, for AP, you don't have to remember that. But basically what that means is that there is one valence electron in a half-filled 3D instead of two valence electrons and 4 electrons in the half-filled 3D. Let's do one more of these, and when we're done doing them, when done doing it, I should say, we can also do its orbital diagram. So let's do the electron configuration for phosphorus, which has the atomic number of 15. It is in period 3, which means that I only go to level 3. I only go to 3 being the first principal quantum number. I'm past helium, I'm past beryllium, I'm past neon and calcium, right? I can follow it on the table. I am past, sorry, that was sodium and magnesium, and aluminum to argon. I don't quite get all the way there. So again, 1, 2, 1s2, 2s2, 2p6, 3s2, 3p3, right? We had to stop there. Now, the noble gas that has an atomic number less than 15 and closest to it is neon. That represents the first 10 electrons, which means we need 5 more, and the other 5 would be the 3s2, 3p3. Now, if I want to do the orbital notation of the last 2 sublevels, this would be the 3s with 2 electrons, and the 3p would each be half-filled orbitals with parallel spins. So we would point them in the same direction. We would never double up before if we have an equal energy, equivalent energy orbital, and not doubling up until we have to in orbitals of the same energy. That is going to be Hund's rule. And so hopefully just going through a couple of different ways that we can do these electron configurations, looking at the periodic table, using the diagonal rule. Hopefully that helped to refresh your memory. Just going to do one more here where we take an ion and do the electron configuration. So let us do SC 2+. Now remember, losing electrons positive, gaining electrons negative. SC has 21 protons. So I'm just going to do SC with no charge first, and SC with no charge. SC is in period 4, right? So we're going to go all the way to 4s2. And then I go 1 into the 3D. Now SC with a positive 2 will lose the electrons from the fourth shell first. The fourth principal energy level is the valence shell, because 4 is the highest principal quantum number. Okay, so those are the electrons that would be lost first. If it was Sc3 plus, we would lose the 3D as well. So hopefully that was a helpful little recap of finding electron configurations just using atomic number in the periodic table. And good luck, as always, my students. If you have any questions, any concerns, please see me in class and ask questions, or stop by and come to Extra Help.